So today I sent an email to all the students in this class. I told them I only see half of the students attending my class. That is much less today. I said I'm not sure what they're doing, but the quiz score very low. Okay, so maybe it's a grading problem. I don't know. Haven't seen it. Okay, I will get it back. But I look at all the quiz scores. Quiz number 9. Only few of them got 15 points. A majority of them like a 4 points, 3 points, 5 points, you know. So I just curious. I talked to the grader. Are you sure, you know, the student don't get so many points? Yeah, he said, I don't know, be careful, you know, maybe there are 3 or 4 solutions to the same problem. Don't just look at my answer key. You know, I give him answer key. Yeah. So I will say that. I will briefly, I will check few of them when I get the quiz back. And to see what's the problem. He said that the student did not give a complete solution. That's the point. Just say it's divergent, then give a very brief reason, which is it's not good enough. So that's why I say you don't give a complete argument. Okay, you have to say something. Okay, even it's very clear in your mind, but you have to express it. All right, so like let's slowly do. We continue to stay in section 11.7 today. Right, and the first problem I want to talk about is this. Okay. So yeah, it's possible I increase the power n squared to n cubed, maybe, yeah, and yeah, so then the convergence will be different. So think about this, right? Do you have any idea? Suppose this is a problem on the test. Are you ready? Okay. For all of today's problems, I give you few minutes, few seconds, you know, 20 seconds to think about. I hope it came up with some idea. You don't need complete the solution. All right. When you see sine 1 over n squared, you should recall this fact. Okay. In other words, if theta is very small, then sine theta is almost equal to theta. Okay. Right? Because the ratio is going to be almost equal 1. Right? For small. So because right now 1 over n squared could be very small. So in other words, this n sine 1 over n squared is very small to, right? It's very close to that. Okay, it's possible. We just assume that, right? So that's my Bn. Bn is just 1 over n. So let's take the limit n over Bn. Now the reason we can use a limit comparison test is because all the terms positive. Because sine n changes signs. The sine 1 over n squared, because 1 over n squared is very close to 0, so sine of that will be 0, positive. All right, so let's take a look. N sine 1 over n squared divided by 1 over n. Okay, so so I think I can move n to the denominator, so I get 1 over n squared sine 1 over n. Okay, so clearly the limit is going to be 1 because 1 over n squared is going to approach 0. Okay, this approaches 0, that approaches 0. So the answer is what? So that means I can use a limit comparison test to check the convergence of the series using the new series. Okay, so the new series is going to be the harmonic series. This is the divergent. Okay, you have to say that complete. You say otherwise take the point off. Why it's divergent? You have to mention. You can say this is harmonic series is already proved, right? Or by the P series test in general. Okay, P equals 1. Because if you look at the P series test, yes, it says that if P is less than or equal to 1, it's a series is divergent. Okay, then this series is convergent, is divergent by the limited comparison test. So this will be the complete solution. Otherwise, if you just say divergent and then you do some computation, but you do not point out, okay, which test you're using, then you lose a point by the limit comparison test. Okay, so this will be the complete solution. First of all, you identify the BN. If you think that you can use the limited comparison test, then you find the limit. Okay, then you said the series you find out is divergent by some test. Okay, so this is this is a complete solution. Okay, so when you get home, you review these problems, don't look at solution, and you write down all the steps and compare mine. Okay, anything missing? Okay, maybe the idea is clear to you, similar, but do you miss any part of the solution? Okay. All right. The second problem is this. Yeah, the above problem I do not have as a method to use. Limited comparison test is best. For this one, I do have a couple methods to show this convergence. All right. So first of all, n squared compared to 5 to the n can be ignored. Think about that. Okay, they are not a different. They are growth at a different rate. Difference. Okay. Just yeah. So clearly this is going to be convergent, but I have to show that, right? You have to show that, and now you can use a comparison test. Okay, you can use a comparison test. You can use a limited comparison test. You can use a ratio test. You can use a load test. Okay, convergence, right? So let's try all the different ways, right? So you use a ratio test, use a comparison test, then you do need to get a rough estimate about like n should be less than or equal to the power n, something like that. You need something like that. Otherwise, you cannot get rid of n squared in the numerator, right? If you just only one there in the numerator, then you get the geometry series, right? That's convergent because I equals 1/5. But if you have a n squared plus 1, you have to get rid of that. But you have to find the upper bound. What kind of upper bound you can find out, right? And as long as the upper bound, the numerator is less than 5 to the n, then you're fine. What I can do is I can freely enlarge this. I can say this first, right? 1 is less than n squared, obvious. And then how about n squared, right? N squared, n less than or equal to n, so n squared is less than or equal to 4 to the n. 4 is okay, 4 is still smaller than 5. So that's why it's 2 times 4 to the n, 5 to the n. So it's constant, and 4 over 5 to the n, we're okay because this 4 over 5 is a smaller than, this is my bn, right? is smaller than 1. So first of all, this is a convergent, okay, by the geometric series. I call it test, okay, and I equals 4 over 5, which is less than 1. You have to indicate that. The two type of series. One is the geometric series, one is the P series. Okay, yeah, we know that convergent. Those are two special series, and we know the result. We just use that. Okay, then implies sigma n star from 1. This is a convergent by the comparison test. I have to indicate n should be positive. It should be non-negative. Otherwise, you cannot use the comparison. Okay, this will be the complete solution. Okay, but I said that it's not easy to get. Not easy to use a limit comparison test. Okay, then yeah, then we use we're trying to use a ratio test. Okay, whenever you see exponential function, you can try to use a ratio test or Roche test. So when you see, you should have another notebook about the summary of ideas. Okay, so you put some notes here. Oh, okay, for the nth term, if you see there's a power function, exponential function, trying to use a ratio test and nth Roche test. But if you see n factorial, probably can just use a ratio test, because if you use a Roche test, nth root of n factorial, I cannot handle it. Okay, so let's try to use the ratio test. Then what do you get? It's n plus 1 square plus 1, 5 to the n plus 1, n square plus 1, 5 to the n. Yeah. Okay. You just turn the denominator upside down. I know there are still some students make mistakes in simplifying this ratio. Okay. So 5 and 5 should be together. And this will be 5 to the n divided by 5 to the n plus 1 to 1 over 5. So this part, the limit is 1. Okay? This part, the limit is 1. It's obvious because in the numerator, this leading term is n squared. Denominator, the leading term is n squared. Both approaches infinity. That cancel out, So the limit is 1/5, which is less than 1. So that means this series, okay, which is the same as this because it's always positive, is convergent by the ratio test. Okay. Now, can you prove normally, as long as there's no n factorial, you can always use a Roche test to get the same result. Okay. If there's n factorial, I can ratio test only ratio test works. So let's try the Roche test. Try the Roche test. Okay. And this is going to be right. It works. Okay. The question is, how can I find the nth root of the numerator? Right? The denominator is the nth root of 5 to the n is just 5. Now the numerator, the limit is going to be 1. Now how do you show that? You just take n square out. Okay. You take n square out. Or you can say it's this is n square out, right? So n square out, and this 1 plus 1 of n square. Okay, I think the second term approaches 1. The first term approaches also 1. Okay, so let's talk about this. Let me claim this is 1/5. It's good. Okay, I'm going to go back to the numerator later. So this implies, which is the same as n, is convergent by the root test. Now the question is, why the numerator approaches 0? Approaches 1, yeah, the numerator. This one, I know that, right? This is this n2, right? So that is going to be n to the 2 over n. That's going to be n to the, that approaches 1 square, which is 1. Okay, no problem. We use, in fact, n to the 1 of n. But how about this? How about 1 plus 1 over n squared? Oops. All right. All right. How about this? Okay. This y's limit is going to be 1. It's not easy to prove that. Okay. But this is a clearly, yeah, this is how do we do that, right? So 1 plus 1 over n squared is less than equal to greater than equal to 1, right? Okay, that's one way to prove. So 1 to the nth power is less than equal to, okay. And this is always equal to 1, but this approaches 1, okay? Yeah, 2 to the 1, because why it approaches 1? Because it approaches 2 to the 0, right? 2 to the 0 is 1, okay? So that's why both approaches 1, so the one in the middle approaches 1 by Swiss level. It's a little bit complicated. If you want to use a ratio test, you have to give a proof. If you don't want to give the proof, you lose a point. Okay. If you use a ratio test, you don't need to prove these 2 factors. Okay. This part is known, right? But the second part, yeah, why this approach is 1? Okay. Why? Right? You have to give it a reason. Okay. Any other method you can use? Other methods? No, I don't think so. Okay. Let's look at the problems from the book. Okay. This is problem number 32. I found out. Okay, it's going to be n factorial to the nth power, n to the 4th. Okay, now when you look at this, well, I see n factorial. So remember, if it's a n factorial, I have to use a ratio test. But there's also n factorial to nth power. So I try to use a ratio test, then I cannot simplify it, honestly. Okay, so I should get rid of the nth power. Then I should use a root test. Okay. When you use a root test, okay, anyway, it's positive. So it's going to be n factorial to the nth power, right? N to the 4n. So you divide this, its numerator is n factorial. The denominator is 4n over and that's just 4. Okay. Now, what is this limit? This limit is obvious. It's infinity. Why? N factorial. This is usually. Okay. N factorial y must be must go to infinity. Let's have 4 terms. Okay. So it's this is a 1 times 2 times 3 times, right? Many terms. Here's n. N minus 1, n minus 2, n minus 3. Then you have n minus 4, right? And then here's n, and you only have 4n here. Okay. So this part is okay when n is infinity. This part approaches 1. But how about the other vectors? Other vectors getting longer. It's getting larger, right? So clearly, this goes to, yeah. If you have to write this, you get like n minus 4 factorial times n minus 3, n minus 2, n minus 1, n. And this approaches positive infinity times 1. So it's positive infinity, okay? As n approaches infinity. So the L, this limit, right, equals L greater than 1. Infinity is greater than 1. So it implies it's divergent. It's divergent by the ratio, by the Lote test. Lote test. Okay, and this for this particular problem, the ratio test does not work. Comparison test maybe works, but it requires comparison requires more math skill. Okay, it's not easy. You have to compare. You have to compare. Okay, and you can try now. If this is n, right? You know it's going to divergent, so it's going to be n factorial over n to the 4th power n, right? And again, for the same reason, if we expand it, it's going to be like this. 1 times 2 all the way to n minus 4, and here's n minus 3, n minus 4, 2, n minus 1, and n, right? But this term goes to 1. This term goes to infinity. So for sufficient large n, this product inside will be larger than 2. So just larger than 2. For n greater than equal to 100, for example. Okay, you can check that. Okay, so just like now, because you have n minus 4 terms in front of it, right? 1 times 2. This number is huge, and the last part is always close to 1. Because the ratio. So definitely the product will be less than 2. Then clearly this goes to infinity. Okay, this goes to infinity as n approaching infinity. Then what? Then the limit of n, right, is going to be infinity. Okay, which is not going to be 0. So it's divergent by the divergence nth term test for divergence. So you have to say that. You cannot just say divergent. It is divergent by the nth term test for divergence. Okay. By the nth term. Right. So you can use this. There are a couple ways to solve the problem. As long as you can prove the nth term does not approach the 0, then it's divergent. But you have to say that by saying by which test you're using, right? Okay, otherwise it's incomplete solution. Okay. This is the number 34. Okay. I give you 30 seconds to figure out the ideas. Okay. The second is over. We have ideas. Comparison. But first of all, you get a rough estimate. It's divergent and convergent. Which one you want to compare? Okay. Comparison test, right? So n plus n cosine square n is n 1 plus cosine square, right? But that number is between, this is always between 1 and 2. Okay, so that means it's less than or equal to n, greater than or equal to n. So now you get a rough idea, right? If it's in the denominator, and this is less than or equal to 1 over n, greater than or equal to 1 over 2. Okay, it's bounded by 2 harmonic series. And you know harmonic series is divergent. So clearly it's divergent. Okay, I probably just use this part is enough. Okay. So this is yeah, you can say that it's from n plus n cosine square n is greater than or equal to, and that's the infinity. Okay, this is by the P series test. Okay, P series test, you know. Okay, so anyway, you compare with the harmonic series. So by the P series test was P equals 1, and then therefore it is divergent. Yeah, we are using by the comparison test. Okay, we are using the comparison test. Now the limit comparison test does not work in this case. The reason is you cannot figure out the limit. Okay, because cosine n, cosine square n to be changed. You don't know the exact value. It's hard to tell. Okay, so the limit comparison test doesn't work. You have to use a comparison test. Yeah, if you choose Bn to be 1 over n, and how do you find the limit, right? So let's say let Bn to be 1 over n, then yeah, and the n is going to be like this, right? Then how about the limits? If you look at the limit, and this is going to be, I think n cancels out, but this one doesn't have a limit. Okay, it does not convert into any number. I know this is between 1 and 1/2, but it does not approach any number, so I cannot use cannot quote the limit comparison test. Okay. Remember, right? We know n approaches infinity of any of this number is going to be 1, right? Clear, right? The reason is a to the 0 is 1. This here, a can be any number. A is between 0, any number. Okay, a is usually is not equal to 1, and when a equals 1, of course, it's always equal to 1. This is the important fact, right? I know it's going to be 0, but I don't know how much. I know it approaches 1. How quick it approaches 1, we don't know. But how about this series? A to the 1 of n minus 1. Okay. So you can assume that a is greater than 1. Doesn't matter, okay? It's not a big deal. Just assume a is greater than 1. Do you think it's convergent or not? Because the nth term right now, the nth term is a to the 1 of n, right? It approaches 0. So you cannot use the nth term test for divergence to say it's divergent. But if this n approaches 0 very fast, this series is going to be convergent. But how fast? We don't know. Maybe not that fast, right? Maybe not that fast. Okay. If you want to use a comparison test, you have to find some series to compare with, right? So I give it 20 seconds. Oh, first 30 seconds, trying to find some ideas. Yeah, we can guess, by guessing, right? I guess. Okay. And let's try to see whether this has a limit. For example, like this. Okay, right? I think this has a limit. This gives you the derivative when x equals 0. Okay, yeah. So this is just natural grade. Okay, it's a positive number. This is a positive number. Okay, if a is greater than 1. I think we should know that fact, right? Then that's enough. Okay, that means a to the x is almost equal to x, right? When x is small, of course you multiply by constant. Okay, so when x equals 1 over n, you know which one you want to compare with that. So you let Bn to be 1 over n. Okay, then limit as n approaches infinity, n over Bn, a to the 1 over n minus 1 over n, right? This is going to be natural log n. Okay. So you do find a simple series which you can compare with. Okay. But this Bn is not good. Okay. This is a divergent. Okay, by the P-series test. Okay. So that means this series is divergent by the limit comparison test. Now, if I change the problem a little, if I put another problem on the test, then this is probably convergent. What I want to say that you're trying to prove this, okay? This series, a to the 1 over n to the power p. Okay. This is convergent if only p is greater than 1. If and only if p, that's just like a p-series test, okay? Because you actually use a p-series to compare. You compare it with a p-series, right? Okay. Of course, I assume that here is greater than 1, okay? I don't have other method for this problem. Limit comparison test is the only way to solve the problem. If you use a ratio test, does not work. Okay. How about the next one? Natural log of n to the power natural log of n. Whoa. What I'm going to do with this? What method I'm going to use? How fast it grows, the denominator. If it grows fast enough, probably it's convergent, right? And I don't know, because natural log grows not fast, but the power is big. Okay, if I have it's a natural log n grows much slower than n. But this probably make a big contribution, because we know this will be convergent. You know, this is a convergent of p greater than 1, right? This is a convergent. So the p is fixed, but here the p is natural log n. Yeah, that's good part. But the negative, the bad part is natural log n. Natural log n is much smaller than n. So I'm still not sure this is a convergent if p is greater than 1, right? Still, I'm not sure this is a convergent at this moment. What method I'm going to use? Right, so far, we don't have any other method, but always it works. You can use a load test as so the nth term approaches 0. So the nth term test for divergence inconclusive. Okay, this approaches 0. We know that. Okay, but the problem, we cannot use the integral test. It's so complicated. It's no way you can evaluate integrals, the corresponding integral. Okay. All right, so it's decreasing, clear, okay, and it's decreasing. So maybe you can use, yeah, then you get a corresponding function. So f of x equals natural log of x to the x, to the natural log of x. My question is, are you able to evaluate this integral, or you prove this integral is going to be infinite? Okay, right? So you try. Okay, let's try. No, I'm not sure it works or not. Okay, the substitution, let omega to be natural log of x, right? So d omega is going to be 1 of x dx. So dx is going to be x d omega. X is e to the w, right? Yes. Okay. So this integral is going from natural log of 2 to infinity, and you will get w to the w and e to the w dw. Got it? I think it's going to be convergent. Can you see that? Why it's convergent? But you cannot evaluate this integral, but this integral you can use a comparison to show. Double check over my dx is going to be x times dw, right? And the x is going to be e to the w. Now, the reason, right? Look at this. This looks like an exponential function, but the base is getting smaller and smaller and smaller when w is large. So how about like this? For w greater than equal to, how about 2e? How about like that? Just choose a number. Then e over w is less than equal to 1/2. Okay, so that means the integral from 2e, not from natural log of w, okay, e to the w is less than equal to 2e and 1/2 to the w. This is a finite, okay? This is a finite, okay? And okay, this is a convergent. This integral, you know, when you're trying to prove whether improper integral is convergent, you can also use a comparison. But here, I have to look at from 2e to infinity instead of log of 2, because log of 2, you know, yeah, it doesn't matter where you start, okay? So this is a convergent, right? Yeah, it's easy to evaluate. This is because of its 1/2. So that implies integral test works. Okay, that implies Yeah, this one, okay, this one is convergent, okay? And then this implies what is the original test, right? It's gonna be natural log of x, this x dx is convergent, okay? If it's convergent, then the corresponding series is convergent, okay? Okay, by the integral test. I have a sense this is a convergent because the power, natural log of n, the power is getting larger. Okay. Another way to look at this problem, this is a little bit more complicated, but speaking of the power, right? Natural log of n to the natural log of n. Okay. You see, natural log of n definitely is greater than, you can make it greater than e. But e to the natural log of n is the n. That's not good enough. Okay, this is definitely natural e to the natural log of n, right? Because if natural log of n is greater than e, right? But that's not good enough. That's not good enough. You get a harmonic series. So how can you get like n squared, right? Right? Yeah. Okay. So that gives me some idea, but that's not good enough because then use a comparison. Then this is going to be less than 1 of n. But I cannot show this conversion because it's less than less than equal to 1 of n, but this harmonic series is still divergent. I want the other one is 1 of n squared. Then you go back, you modify. Okay, why? If you put, how about like this, right? Right? Then that becomes square, right? Then you put it into the denominator. But you wanted to make this one, then you just need to say this is greater than or equal to e squared. Okay, it's modified, right? So if natural log n is greater than or equal to e squared, then you have this comparison. That's good enough. Okay, and since this is it doesn't matter from any number, right? Since this is what is this? This number you can estimate. This number is definitely e squared is less than or equal to 9. Okay, because e is less than 3, e squared is less than or equal to 9. So as no, that's not good enough because I have to figure out what is n. N is greater than or equal to e to the e squared 1. This number is not that big. Okay, maybe still less than 100. Okay, so you can say some capital N, right? This is divergent, is convergent. Okay, and so this implies is convergent. Okay, by the comparison test. But the difficult part is to figure out this is inequality and for which n. N must be sufficient large. For example, n should be greater than e to the e squared. Let's get rough estimate. What is e to the e squared? Okay, e to the e squared less than or equal to e. E is less than 2, less than 3, so 3 squared is 9. less than or equal to 3 to the 9th power. Right? I don't know, it's a very large number, 3 to the 9th power. That's okay, 3 to the 9th power. How big is this number? Okay, 3 squared is 81. Okay, yeah, you can say that 3 to the 4th power, 3 to the 4th power, 3 squared. So this is 81, 81, 10. Okay, just put 50 there. Okay, that's a number. Okay, so what I want to say that you have this is going to be n less than square for n greater than that. Doesn't matter, right? Some large number. You can ignore all the 100,000 terms in front of that. Convergence is independent of the finite many terms. Right? Yeah, because this is a guarantee it's greater than e to the e squared. Okay, that's the reason. If you like integers, if you don't like e to the e squared. All right, this is my favorite example. I give you 2 seconds to figure out how many methods you can use, apply to this problem. I may give some extra credits on test 2, but extra credits will be like that. If you can find another method, okay, right on the back side of the page, and I give the extra credits. Okay, if you cannot figure out the second method, then instead you don't get extra credits. Yeah, I'm worried about you're not going to get your scores on the second test, so I have to give extra credits. Yeah, I will look at the quiz scores first. Okay. Because the difficulty level of the problems will be similar to the problems of the quizzes. All right, for this problem, at least I have 2 methods I can apply to prove this is convergent. Okay, the ratio test and row test does not work because there's no explanation here. There's no n factorial term here. Okay, if you use a ratio test, load test, the limit is always going to be what? It's inconclusive. Okay, you cannot get any credit. If your limit is 1, then you say it's convergent. That means number 1, you don't know what is ratio test, because ratio test tells you clearly inconclusive. You still conclude this is 1, that means you're really not good at all. Here, this for this type of problem. So if you're like a lawyer, you quote the law in the court, but that law does not imply that person is guilty. Then you say this is guilty, right? So that means you're not qualified to be lawyer. Anyway, so let's do this problem, right? Alternating series. So try alternating series test first. Okay, try alternating series test first. So this is a Bn. You let Bn to be n squared plus 1, and then clearly Bn is positive. Bn goes to 0. The question is Bn is decreasing? Okay, so here's f of x. Okay, so you have to look at the derivative of the function. If it's decreasing, the derivative is negative, it's decreasing. Okay. All right, so find the derivative minus square root of x and 2x. Okay, well, how can I simplify? Well, you take square x, you put in the denominator. So you only have x squared plus 1 here. But then you get 2 square x is 2x times 2x. Okay? So you get 1 minus 3x squared. I think clearly it's negative if for x greater than or equal 1. Right? When x greater than or equal 1, definitely it's negative. So it's decreasing. No problem. So f of x decreasing, that implies bn decreasing for n greater than 1. Right? So this series is convergent by alternating series test. Right. But actually, you can prove this much easier way to prove this is convergent. Not only convergent, absolute convergent. Right, let's go back to the problem, right? Right, you take a look at the absolute value of this. Then this, right? And then because the numerator denominator n squared, so you can then that's n to the 3/2. And the p series, you simplify, you can get upper bound, which is series, p series. So p series, this is a convergent, okay, by the p series test. Okay, for p greater than 3/2, which is less greater than 1. Okay, p is greater than 1. Then this implies not just the original series. This implies that the series with a positive term is convergent. Okay, by the comparison test. Then you can conclude that the original series is convergent. Actually, not only convergent, it's absolutely convergent. Okay, then you can conclude, because you have to answer this question whether the original series is convergent, right? So this is absolutely convergent. Okay, this is a complete argument. This is a complete argument. Absolutely convergent. But we do not prove it's absolutely convergent. So just say it's convergent. But you could answer it's absolute. That tells you you know more than what I need. Absolute convergent. Right? Right? Right. Yeah. So when you go home, before you do the homework, go through all the examples in the cover the solutions and cover the solutions, trying to figure out all the possible solutions you can get. Right? Any other method you can use? I think that's it. The comparison test, the ratio test, and the load test does not work. All right. How about one more problem? 2 to the 1 of n squared. Okay, n starts from. Okay. I think this is a convergent. and it's convergent. You can use any methods. Okay. The reason is the limit of 2 to the 1 of n is going to be 1. So this series, the numerator is, yes, the numerator changes, but it's almost equal 1. Okay. This is the important fact. 2 to the 1 of n equals 1. Then you can, and then we also know that there's 2 facts, right? We also know that this is convergent, right? So this is 2 facts convergent. Okay. 2 facts. Then how can I use these 2 facts to prove it? I can do the following. The first method. I use a comparison test. I'm not going to use a limit. The limit 2 to the 1 of n is going to be 1. So this number is getting smaller and smaller. Actually, this number is always less than or equal to 2. Do you agree? For any n? That's it. Then it's easy. This is a by the comparison test this series. Yeah. So then this is a convergent by the comparison test. Okay. I did not because I already stated that. Okay. So that's the reason. Otherwise, I have to say this is the series on the right hand side is convergent. Okay. Right. Now you can also use the limit comparison test. Let n to be 2 to the 1 of n square, and bn is just 1 of n square. Then the limit, okay? As the limit should be equal to 1, I'm pretty sure. So when you divide, it's going to be just 2 to the 1 of n, which is 1. So those 2 series have the same convergence. Right? Have the same convergence. And since bn is convergent, sigma bn, so this implies this is convergent by the limit comparison test. Right? That's it. So we have done all the exercise.